So guys, we have already discussed about how induction motor works. Now welcome to my fourth lecture on induction motor. In this video I am going to describe you what is sleep, what is the relative speed between the stator field and the stator winding, the relative speed between the rotor field and the stator winding, what is the relative speed between rotor and the stator winding. Apart from these, we are going to draw the equivalent circuit of induction motor, and we also derive the equation of air gap power. So let's start.
Now the stator field is moving at a speed ns, that is synchronous speed, equal to 120 F by P. Let's assume the speed of the rotor equal to nr, which is less than synchronous speed, because induction motor is a asynchronous machine. The relative speed between the stator rotating magnetic field and the rotor is called sleep. So sleep is equal to ns minus nr divided by ns. As the stator winding are stationary and stator flux is rotating with a speed of synchronous speed, then the speed of the stator flux with respect to the stator winding equal to ns, synchronous speed, that is equal to 120 F by P. Now the speed of the rotor winding with respect to the stator winding equal to nr, we have already assumed, and nr equal to 1 by 1 minus s into ns. Now the speed of the stator flux with respect to the rotor winding. Stator flux is rotating at the speed of ns and rotor winding is rotating at the speed of nr. So speed of the stator flux with respect to the rotor winding, that is equal to delta n equal to ns minus nr, that is equal to s into ns. This relative speed between the stator flux and the rotor winding is responsible for generation of rotor EMF. So the frequency of the rotor EMF equal to this relative speed into number of pole divided by 120, that is equal to ns minus nr into P divided by 120, that is equal to SF. The rotor flux has a speed with respect to rotor winding equal to 120 divided by P into the frequency of rotor EMF, that is SF, equal to SNS, because this rotor flux is generated due to the rotor EMF and the rotor current. So the total speed of the rotor winding and the rotor flux is 1 minus s into ns plus s into ns, that is equal to ns. So rotor flux has a speed with respect to the stationary stator winding is ns. Stator flux also has a speed with respect to the stationary stator winding is ns. So relative speed between the rotor flux and stator flux is 0. Let's see this example. A 3-phase 440 volt 6-pole 50 Hz squirrel cage induction motor is running at a sleep 5%. Calculate the speed of stator field with respect to stator winding. Calculate the speed of rotor with respect to stator winding. Calculate the speed of rotor field with respect to rotor winding. Calculate the speed of the rotor with respect to stator winding. So the first point is we have to calculate the speed of the stator field with respect to stator winding, that is equal to synchronous speed 120 F by P equal to 1000 RPM, revolution per minute. Now we have to find the speed of the rotor field
with respect to rotor winding. We know that frequency of the rotor field equal to SF. So the speed of the rotor field with respect to rotor winding will be 120 divided by P into SF, that is equal to S into NS, equal to 50 RPM. Now we are going to calculate the speed of the rotor with respect to stator winding, that is equal to 1 minus S into NS, equal to 950 RPM. Now we are going to calculate the rotor flux speed with respect to stator winding, that is equal to speed of the rotor flux with respect to rotor winding plus speed of the rotor with respect to stator winding, that is equal to 1, so SNS plus 1 minus SNS, equal to 950 plus 50, that is equal to 1000. So we can conclude that rotor flux has a speed same equal to the stator flux with respect to stator winding.
Equivalent circuit of an induction motor enables the performance characteristics which are evaluated for steady state condition. An induction motor is based on the principle of induction of voltage and currents. The voltage and current is included in the rotor circuit from the stator circuit for the operation. The equivalent circuit of an induction motor is similar to that of transformer. Stator circuit model. The stator circuit model of an induction motor consists of a phase winding resistance R1, stator phase winding leakage reactance X1. The no-load current I0 is simulated by pure inductance X0, taking the magnetizing component I mu, and non-inductive resistance R0 carrying the core loss component IW. That's mean no-load current I0 equal to I mu plus IW. The total magnetizing current I0 is considerably large in case of induction motor as compared to that of transformer. Why it is large? This is because higher reluctance caused by the air gap in the induction motor. The flux of the stator has to cross the air gap to cut the rotor. We know that reluctance of air is more than that of core material of the transformer. As we know that in a transformer the no load current varies from 2 to 5% to the rated current, whereas in an induction motor the no load current is about 25 to 40% of the rated current depending upon the size of the motor. The value of magnetizing reactance is also very small in case of inductance motor. Now we will study about rotor circuit model. When a three-phase supply is applied to the stator winding, a voltage is induced in the rotor winding of the machine. The greater will be the relative motion of the rotor and the stator magnetic field, greater will be the resulting rotated voltage. The larger relative motion occur at standstill condition, because at standstill condition the rotor is stationary and the stator flux is rotating with a synchronous speed. Thus in this condition is also called block rotor or locked rotor condition. If the induction rotor voltage at this condition is E2, then the induced voltage at any slip is given by E2 equal to SE20. The rotor reactance is constant and is independent of slip. The reactance of the inductor motor depends upon the inductance of the rotor and the frequency of the voltage and the current in the rotor.
If L2 is the inductance of the rotor inductance is given by x2 equal to 2 pi f2 L2. As we know that rotor frequency equal to S of stator frequency, that is f2 equal to S f1. Therefore x2 will be 2 pi S f1 L2, that is S into 2 pi f1 L2, that is equal to S into x2 naught. x2 naught is the standstill reactance of the motor. The rotor impedance is given by the equation Z2S equal to R2 plus JX2S, that is equal to R2 plus JS x20. The rotor current per phase is given by the equation I2S equal to E2S by Z2S. Now putting the value of the Z2S, we get this equation. Here I2 is the slip frequency current produced by the slip frequency induced voltage SE2 naught acting in the rotor circuit having an impedance per phase R2 plus JS x2 naught. The rotor equivalent circuit has a frequency of SF1 and stator equivalent circuit has an frequency of F1. Two different frequency circuit cannot be added to form a complete equivalent circuit. To get the same frequency of both the equivalent circuit, we have to divide the rotor equivalent circuit frequency with S. As we dividing the frequency of rotor equivalent circuit by S to get it F1, we have to divide all the parameters of rotor equivalent circuit with S. Now dividing the equation of I2S by slip, we get the following equation. R2 is constant resistance and the variable leakage reactance SX20 in the previous equivalent circuit, but in the new equivalent circuit has a constant leakage reactance X20 and a variable resistance R2 by S. This equation explains the secondary circuit of an imaginary transformer with constant voltage ratio with same frequency of both sides. The imaginary stationary rotor carries same current as the actual rotating rotor. This makes possible to transfer the secondary rotor impedance to primary side. The equivalent circuit is further simplified by shifting the shunt resistance R0 and X0 to the input terminal as shown in the figure below. The approximate circuit is based on the assumption that V1 equal to E1 equal to E2 dash. In the above circuit, the only component that depends on the slip is resistance. All other quantities are constant. The following equation can be written at any given slip by this. Putting the value of Z, we get the equation of I2 dash equal to this one. In the equation of I2 dash, we find there is a J. So I2 dash is a complex quantity. It has a magnitude and also has an angle. This angle is power factor angle of the current I2 dash. This power factor angle phi 2 dash and the power factor cos phi 2 is given by R1 plus R2 dash by S plus Z dash. No load current I0 is given by I0 equal to I mu plus I W. We have already discussed about this. So voltage across the shunt branch is V1. As the V1 is current is applied to the stator winding of the induction motor. So current I mu equal to V1 by R naught, as voltage across the R1 is V1. So the current I mu will be V1 by R naught. Similarly, voltage across X naught is V1. So I omega equal to V1 by IW equal to V1 by J X naught. So total current I naught we will get equal to V1 by R naught plus V1 by J X naught. The rotor of the circuit is drawing the current I2 dash, and the magnetizing components are drawing current, no load current, that is I naught. These I2 dash and I2 both come from the stator equivalent circuit. That is why, according to Kirchhoff's current law, I2 dash plus I naught equal to I1. Now we will consider the loss. The core loss consist of hysteresis loss and eddy current loss. Eddy current loss happens because of eddy current in the magnetic material. We can reduce eddy current loss by laminating the core. Hysteresis loss can be reduced using the proper core material and using some impurity with it. Now this core loss is given by 3V1 I naught cos phi naught. This 3 is coming for 3 phase. We are considering single one phase. If we have to calculate, we have to multiply with 3. V1 is the voltage across the magnetizing component, and I naught is the no load current that is flowing through the magnetizing component. Cos phi naught is the power factor angle of the no load current. We are giving voltage V1 and I1 to the stator input, and the power factor of this is cos phi 1. So stator input equal to 3V1 I1 cos phi 1. This stator input 3V1 I1 cos phi 1 is contributing the core loss
and the copper loss and the mechanical equivalent of the rotor circuit.
That is 3V1 I1 cos phi 1 equal to core loss plus 3V1 I2 dash cos phi 2. 3V1 I2 dash cos phi 2 is the copper loss in the circuit. So this can be written that 3V1 I2 dash cos phi 2 equal to 3 I2 dash whole square plus R1 plus R2 dash by S, as copper loss occurs only in the resistors, not in the inductors. So the power which is get after considering the core loss, that is called air gap power. So air gap power per phase is V1 I2 dash cos phi 2, that is also equal to I2 dash whole square R2 dash by S.